Before we learn how to integrate all rational functions, we will review the basic vocabulary and the properties. First, let's recall what a rational function looks like. Rational functions are ratios of polynomial functions. When polynomials in the numerator and the denominator are both written in standard form, then such rational function is said to be in standard form. In standard form, we can easily read the leading coefficients and the degrees of the polynomials in the numerator and the denominator. If the degree of the numerator is less than the degree of the denominator, then such rational function is called proper. Otherwise, it is called improper. Improper rational functions can be rewritten in quotient form by performing a long division on polynomials. In quotient form, we can identify the quotient, the remainder, and the divisor, which are the polynomials and therefore have their own degrees and leading terms. Let's practice writing an improper rational function in quotient form. We perform the long division of polynomials and use the quotient, remainder, and the divisor to put the results together in quotient form. Let's practice writing another improper rational function in quotient form. We perform the long division of polynomials and use the quotient, the remainder, and the divisor to put the results together in quotient form. Let's practice writing one more improper rational function in quotient form. We again perform the long division of polynomials and use the quotient, the remainder, and the divisor to put the results together in quotient form. When polynomials in the numerator and the denominator are both written in factored form, then such rational function is said to be in factored form. When a rational function is written in factored form, we can easily read the zeros and their multiplicities in the numerator and the denominator. Of course, for each polynomial, the sum of all multiplicities adds up to the degree of the polynomial. If the numerator and the denominator have no common factors, then such rational function is said to be in reduced form. If there are common factors, then we would write the rational function in reduced form by removing the common factors from the numerator and the denominator. Let's take a look at one of the previous examples and see if it is possible to reduce the result. Since the numerator and denominator are both in factored form and there are no common factors, we conclude that the original rational function is now in reduced form. Let's take a look at one of the other previous examples and see if it is possible to reduce the result. We factor the numerator and denominator and reduce by the common factor. Now we conclude that the original rational function is in reduced form. Let's take a look at the last example and see if it is possible to reduce the result. We factor the numerator and the denominator and reduce by the common factor. Now we conclude that the original rational function is in reduced form. One of the interpretations of the fundamental theorem of algebra is that every polynomial can be uniquely factored into the product of linear and irreducible quadratic factors. What exactly is an irreducible quadratic expression? Irreducible means that it cannot be factored further into a product of two linear factors, which means that the quadratic expression has a negative discriminant. One thing that we can do with all quadratic expressions and irreducible ones in particular is completing the square. We complete the square by adding and subtracting the square of half of the coefficient of x. Here are a few examples of irreducible quadratic expressions and their equivalents after completing the square. Now, using the fundamental theorem of algebra, we can completely factor out the denominator of every rational function. In addition to the fundamental theorem of algebra, there is also the partial fraction decomposition theorem that guarantees that every proper rational function in reduced form can be uniquely decomposed into a sum or difference of simple rational functions whose denominators are linear or irreducible quadratic expressions, possibly raised to some powers. Let's take the last look at one of the previous examples and see if it is possible to decompose the result. It appears that the function is in decomposed form. Let's take the last look at one of the other previous examples and see if it is possible to decompose the result. It again appears that the function is already in decomposed form. Let's take the last look again at the last example and see if it is possible to decompose the result. This function can be decomposed into a sum of two simpler rational functions. Using algebraic techniques, we can determine the coefficients a and b. Now the original rational function is decomposed. The goal is to be able to integrate any rational function. Assuming that a rational function is proper and in reduced form, we can use the partial fraction decomposition theorem to decompose the rational function into a sum, and then use the linearity property of the integrals to split the integral into the sum of the integrals of the simpler rational functions. So the idea is simple. As long as we know how to integrate the simple rational functions, we can integrate any rational function. Now that we have reviewed the basic vocabulary and the properties of rational functions, we are ready to learn how to integrate them as an entire class.